Now friends, I'm assuming you must have already figured out the proof of this. More importantly, if not the proof, the formula application is more important. We need to understand how this formula is applied, where all it will get applied. So now we have understood that area of a triangle in terms of the semi-perimeter is nothing but a root of s into s minus a into s minus b into s minus c. Now let's try and see for a general triangle. Now let's say here is a triangle ABC, right? The base is BC. Now if I fix this particular base BC, as you can see, we have fixed this particular base and we have the point A over here. So in this case, the area of a triangle, area of this particular triangle is half into BC into this corresponding height. Now think of it in this direction. Let's say this is some value of A, this is some value of B, this is some value of C. Basically three different sides of a triangle. You can find the area of triangle using this formula as well. So if I try and move this particular point A, the top point, and try to move this point parallelly, as you can see, I'm trying to shift this here, keeping the base intact. I'm keeping the base same. Earlier the point A was somewhere here, now it has moved here. So in this case, what will happen to the area of a triangle, area of this particular triangle rather? As you can see, if I have to apply this formula, then obviously my sides of the triangles have changed now. One side is same, the base is same, but the other two sides have changed. So area of this new triangle might change. But if you think of it in this direction, that the area of a triangle is half into base into its corresponding height, then you will realize that area of both these triangles, the original and the new one, is absolutely same. Why? Because the base is intact, so they have the same base. The original triangle ABC and the new triangle A-BC have the same base BC. So half into BC is still same for both, and the height is also same, because if you see, the height for the original triangle is same as the height for the new triangle. Height is nothing but the altitude which is dropped from the opposite vertex of the base onto the base. So in both these cases, as you can see, the height is still the same, and hence the area of the triangle for triangle ABC and triangle A-BC is going to be the same by the basic formula of half into base into height, because base is intact. So base for both these triangles is same, and the corresponding height eventually is also same. So basically, if I try to move the vertex in a parallel direction to the base, try and think of it this way, the base is intact, the vertex is being moved parallelly to the base, then the area remains the same. So we can make this as an important note to ourselves. If for an area of a triangle, the base is constant and the opposite vertex is moved parallelly to the base, then the area remains the same. Now when you try and find the area of the new triangle in terms of this, we obviously now know that the area of the triangle is going to be the same, but A, B and C are going to change. Rather, one of them is going to remain the same, the base is going to remain the same, but the other two sides are going to change in such a way that the area, the new area, is still the same. So this is the beauty of Heron's formula. Even though the sides are changing, the area still remains the same, because they adjust themselves in such a way that you get the ultimate area as the same value as the original value. So again, the bottom line here is, for a constant base, if you move the opposite vertex in parallel to the base, then the area remains the same.